Hi again, everyone. Welcome back. We've made it through infrared and we're almost at the end. This video is going to cover Raman spectroscopy. Here are some learning objectives for you. It would be worth coming back and looking at these once you've finished watching this video. So here's a good place to start. What is Raman spectroscopy? Well, this first dot point's interesting. It says that Raman spectroscopy is a kind of vibrational spectroscopy. Well, it is a vibrational spectroscopy in that it yields information about vibrational energy levels in a molecule. We can probe the molecular vibrations by doing Raman spectroscopy. What this kind of is referring to is that it uses visible or near-infrared light. So we use photons of much higher energy. And as we'll see in the coming slides, it's possible to use these photons to study the vibrational energy levels of a molecule. We'll also see that Raman spectroscopy is quite complementary to infrared. When we were discussing infrared spectroscopy, we saw that there are some vibrational transitions in a molecule which don't lead to an infrared absorption, so they don't appear in the infrared spectrum. However, as we will see, often these transitions, which are not infrared active, give a very good signal in Raman. So between infrared and Raman, pretty much all the vibrations in a molecule can be studied. So here's an example of this complementarity. Strong infrared signal, weak Raman signal, up there at about 2900 wave numbers. Down here at about 500 wave numbers, we've got some strong Raman signals and little to no infrared absorption. So how is Raman spectroscopy done? Well, it's a scattering experiment. So, a visible or near-infrared light source, usually a laser, is shone upon the sample, so quite a high photon flux usually, and photons are scattered, and it's these scattered photons which are detected. Now, as we saw with near-infrared, when you bring a lot of photons of high energy onto a sample, often you can get absorption, transmittance, and scattering all happening at once. And this is indeed what happens with Raman. And with the Raman measurement, it's the scattered photons that we're trying to collect. That's where the information about the vibrational motions is to be found. So Raman spectroscopy is named after C.V. Raman, physicist in the first part of last century. He got the Nobel Prize in 1930, and he characterized this Raman effect quite extensively. So he shone visible light onto certain molecules and saw that photons were scattered, but that some of these photons were scattered at different wavelengths to the wavelength that he was shining on the sample. Now that in itself is interesting, but can be explained by classical physics. What he saw was that not all wavelengths were scattered. There were only some discrete wavelengths that were different to the incident wavelength that was scattered. So he realized that the process was quantized, and early 20th century, of course, is the period in science when the quantum nature of matter and energy was being discovered and investigated extensively. And so he realized that this was a very important process and a very direct way to demonstrate the quantum nature of matter. It's only a weak phenomenon, and Raman had to work pretty hard to get enough scattered photons to have a meaningful measurement. But nowadays, with high power light sources like lasers, it's become a routine analytical tool. Right, so we have a key concept here. It's flashing at us. If you understand this, you've got the heart of Raman spectroscopy. We are irradiating the sample with visible or near-infrared radiation. This is giving us information about molecular vibrations. The way this is done is the differences in the energies of the incident and scattered photons. That's the key. So we're not so worried about exactly what wavelength we're shining onto the sample, and we're not so worried about exactly what wavelength is being scattered off. It's the difference in those wavelengths that tells us about the vibrational energy levels. So, most photons are scattered elastically. That's Rayleigh scattering. You shine light on the molecule, the photon bounces off. The frequency or wavelength is unchanged. So what we've got here is our excitation frequency, or the frequency of our incident light. This blue line is showing the intensity of the scattered photons. Most of them are here in the Rayleigh peak. Now, some photons are scattered at higher and lower energy. These are referred to as Stokes and anti-Stokes scattered photons. Stokes are at lower frequency or energy, and anti-Stokes at higher frequency or energy. And this is inelastic scattering. Now, it's this energy difference here. Either the energy difference between the Rayleigh and the Stokes, or the Rayleigh and the anti-Stokes, will tell us about the vibrational energy levels. And that's because when the scattering occurs, a quantum of vibrational energy is lost or gained by the scattered photon. So in the case of a Stokes scattered photon, the photon has lost a quantum of vibrational energy. That's this bit here, the energy equivalent to that. For the anti-Stokes photon, it's gained that little bit of energy. Now, to keep everything consistent, the molecule also gains or loses a quantum of energy. So if the photon loses a little bit of energy, that's because the molecule has gained it, and vice versa. If the photon gains it, it's because the molecule has lost it. So let's have a closer look at the energy levels involved in Stokes and anti-Stokes scattering. Now, it's not great, I have to admit, this idea of a virtual state. Some physicists really like them, some hate them. I think I'm leaning towards the latter a bit. I don't particularly like virtual states, but that's just me. They are useful in trying to understand these phenomena. So it's not a real state. So we've been talking about ground states and excited electronic states like S1, S2, triplet states like T1. They're real electronic states. What we're saying here with a virtual state is that the photon is not absorbed. If it was absorbed, if we were going into that real state, then that energy would be taken into the molecule. So if we look at the energy diagram here, we have an arrow heading up. That's the photon, the incident photon. We're getting to this virtual state here. That's the dashed line. But we're not really absorbed. It's just a very, very weak interaction. And then the photon is scattered. It's not emitted or fluoresced or anything like that. It's just scattered. But it's scattered with a little bit less energy. And the bit of energy missing is this bit here, which I've drawn terribly. this little bit here. And the bit of energy missing is equivalent to the energy difference between the ground and first vibrational states. So by calculating the difference in energy between the incident and scattered photon, we've got the energy of the fundamental transition. In exactly the same way, the anti-Stokes scattered photon is here. It interacts with the molecule by going into this virtual state, picks up a quantum of vibrational energy. It's that same quantum of energy, but this is now gained by the photon. And again, the difference between the incident and scattered photons gives you the energy required to go from V equals 0 to V equals 1. So it's these inelastic scattered photons that give us the useful information. But, as I mentioned before, very weak. Probably only 1 in a million photons are actually Stokes or anti-Stokes scattered. That's a tough job to detect such a weak signal. The way around it these days is we use lasers. Lots and lots of photons all at the same wavelength. So until lasers came around about 40, 50 years ago, Raman spectroscopy was seen as a very exotic, interesting phenomenon, but not one for convenient everyday use. But now it is used a lot. And if you want to know more about lasers, put in a little plug for third year Chem 3952. We run a nice little section on lasers in that. So we come to the key point then in Raman spectroscopy. The Raman spectrum plots the difference between the excitation, the incident photons, and the Raman scattered photons. So we take that difference, as indicated here, take that difference, we calculate what it is, and we plot it. And because there's a whole bunch of photons here, these Stokes scattered photons, we get a nice big spike there. This difference, let's say, is 550 wave numbers. Whatever that excitation frequency is, and whatever this Stokes scattered photon frequency is, the difference is 550 wave numbers worth of energy. And that's what we plot over here. That's that value there. Now, there will be some more Stokes photons further out here, and these will be scattered more. Maybe that's about 1,000 wave numbers now is the difference between these photons and the incident photons. This lot are then plotted here, and so on. So whatever the Stokes and anti-Stokes peaks are that you have, you calculate all of those differences and you plot the differences down here in the Raman spectrum. And that's what you get. So if you understand why the x-axis here is given as frequency or delta frequency, then you understand what's going on. The frequency is IR. It's a direct measurement. We're measuring the frequencies where the absorption occurs. With Raman, it's indirect. We're calculating the frequency differences between the incident and scattered photons. We're plotting the delta news there. Okay, we saw with infrared that it's the transition dipole moment that's the key property in determining if a vibration leads to an absorption and therefore a signal in the infrared spectrum. In Raman, it's a bit more complex. There's a lot of factors at work, but the key one is polarizability. polarizability of the molecule. Now, this is an interesting concept. The polarizability is given by this little formula here. And what that means is, so here's the polarizability. That is the induced dipole moment, that's our mu, and the strength of an electric field. So this is similar to transient dipoles when you're talking about interactions between molecules. You talk about van der Waals or dispersion forces. So how when one molecule gets close to another, it can induce a dipole. This is the same idea. When you apply an electric field to a molecule, the electron density around that molecule, or in that molecule, responds to that field. You get an induced dipole. The amount of induced dipole that you get for each bit of electric field, so the value of mu divided by E, is the polarizability. Some molecules get a bigger induced dipole for a given field strength than others. So the extent that that happens, the polarizability, is what determines primarily the intensity of Raman bands. Okay, that last slide was a bit heavy, that discussion of polarizability, but let's see it in action. So we've got two molecules here, mesitylene and indene, and we've got infrared and Raman for both, plotted on the same axes, noting that the x-axis is nu, frequency for infrared, and delta nu, difference in frequency, for Raman. Just by looking at them, we can see lots of examples of where this complementarity comes in. There's a good one here at about 1,000 wave numbers there for indene. We have a vibration which gives a very good Raman signal, barely shows in infrared. And likewise, right next to it, there's a bunch of infrared signals which are not appearing in Raman. And that's because the infrared signals will be due to vibrations that lead to a change in the transition dipole, whereas those Raman signals are coming from vibrational transitions which lead to a change in polarizability of the molecule. Okay, we're now going to take a quick look at how you measure Raman spectra. So what's inside a Raman spectrometer? Well, first of all, you need an intense light source, usually a laser. And a good laser to use, that's often used in Raman spectroscopy, is a YAG laser. It stands for yttrium aluminium garnet. And that's the crystal that's in there, that's the lasing medium. And these can produce intense UV, visible, and near infrared light. So that's shone onto the sample, some wavelength selection so that you block the Rayleigh photons and then detect the Raman photons, and just use a transducer, so that's something which uses the photoelectric effect, photon in, electron out, and that gives you a signal which is then recorded. So fairly straightforward kit items these days. You can also do Fourier transform Raman if you want, but there's plenty of dispersive instruments around. So as we saw in the IR field, pretty much everything is FTIR, but with Raman, dispersive instruments are absolutely fine, and you see them around just as much as you do Fourier transform Raman instruments. The nice thing about the dispersive instruments is that you can measure all the scattered wavelengths by using a large area detector like a camera, a CCD camera. So the Fourier transform instruments, of course, can measure all wavelengths because they've got the Michelson interferometer in them, but the dispersive instruments in Raman also work just fine with large area detectors because we're using visible and near-infrared photons. So we have very good cameras for those wavelengths. So the FT Raman spectrometer looks pretty similar to an FTIR spectrometer, except that here, this is a little catch, here in the Raman spectrometer, the YAG laser is the excitation source. Remember, in the FTIR instrument, there is a laser. Often it's a Heaney laser, but that's used purely for alignment and calibration. It's not the energy source. That's a glow bar or a synchrotron. But in the FT Raman spectrometer, the laser is the light source, goes through the Michelson interferometer, through the sample, and onto the detector. Preparing samples for Raman is actually quite straightforward. Gases can just be stored in a gas cell. To get more scattering, often a nice little mirror arrangement is used so that the incident light actually bounces through or is passed through multiple times to increase the yield of scattered photons. Liquids and solids can just be used in glass containers, no problem. The good thing about Raman is that glass to visible wavelengths is completely transparent. So silica absorbs in the infrared quite a bit, which makes sample handling a little bit tricky. But for Raman, because we're using visible photons, putting your sample in glass is absolutely fine. Sample prep for solids is pretty similar to infrared. You can make them into pellets and study them that way, or you can just use them as is. Often you can just scatter enough light directly off a solid sample. As long as you've got good collection, the thing that you're working against here is that the scattering is pretty inefficient. But if you have good collection, for example with a fiber optic, you can collect the photons directly at the source, at the sample, and feed them into a monochromator and detect them that way. Okay, we're going to finish up now with just a quick discussion of a variation on Raman spectroscopy called resonance Raman spectroscopy. Now, we're using visible light to do Raman, and in the first part of the course, we spent a lot of time talking about fluorescence, which is emission of visible light, usually following from absorption of visible light. So when Raman spectroscopy is done, the incident photons are usually tuned away. So Raman, the incident photons are usually tuned away from electronic transitions, because if you shine incident photons on the sample that correspond to an electronic transition, you're just going to excite the sample and get a whole lot of fluorescence, which is going to completely swamp the Raman signal. But in resonance Raman, that's exactly what they do. They deliberately tune the incident photons to the electronic transition of the molecule. In some setups, often when there are metallic surfaces nearby, this actually can enhance the Raman signal hugely. So resonance Raman can enhance, in the right circumstances, by orders of magnitude the amount of scattered photons. Now the key point here is to see how it's different mechanistically. So the grey arrow here is the incident photon, and we've got our electronic transition shown. That's here, that's the S1 state, and we're exciting into that S1 state. Raman we just scatter straight off. And here's our scattered photon. And this is a scattering phenomenon, and it's really, really fast. That is femtoseconds. Whereas what we were talking about earlier with fluorescence, when we're on resonance with the electronic transition, the photon is actually absorbed. Then there is the vibrational relaxation, and then the fluorescence from the bottom of S1, from that lowest V=0 state. And this process, as we saw, is typically nanoseconds. So that's the key difference there between Raman and fluorescence. Raman is scattering, fluorescence is absorption, then emission. And usually Raman is done by staying away from these electronic transitions because the fluorescence will swamp the Raman signal. But sometimes going on resonance can really help the measurement. Okay, there we are. Here's a short summary of the key points. And as I said at the start, it might be worth going back and having a little look at the learning objectives at the beginning.